like I said, the chain rule is going to be really important for us. This concept is it's a little bit tricky at first, but if you get the idea, we're actually going to use the same idea of the chain rule for a few different things that we're going to do throughout the year, with not only differentiation but also with integration, and some other stuff. So there's two functions that I have graphed here. The one in black is the sine of x squared, and the one in blue is, at this point, what most people would probably guess is the derivative of the sine of x squared. Because the derivative of sine is cosine, right? So if we have the sine of x squared here, then a lot of people would guess that the derivative of sine of x squared would be cosine of x squared. I want somebody to tell me why cosine of x squared is not the derivative of sine of x squared. Cole?
Well, because right at the beginning, like sine of x squared is slope, is like at the point of the origin.
Okay.
It's not 1, because that's what.
Okay, good. So a very quick way to notice it, the slope here is 0. So the derivative should have a point at 0, not at 1. Okay, how about something else? Vimal?
It's the square of the x, not the sine. Sine squared it.
Yes. That's true. So how do we know that cosine of x squared isn't the derivative?
You're squaring a value in the trig function.
It's true. Any other ideas? Looking at the graph here. How about right here? The slope of the function, the f of x function here is what? Negative. So that means that the derivative should be negative. In fact, if I just go through and I look at where the derivative should be positive or negative on this graph here, I'm going to have a 0 there, I'm going to have a 0 there, I'm going to have a 0 there, and a few different places here. So so in this interval here, the function is decreasing. It's got a negative slope, so we would expect the derivative to be negative. And on this interval, we would expect the derivative to be positive. Then it's going to be negative here, and then positive here. And so our derivative graph is not matching up with those exactly the way we think they would. Actually, to the right of the origin, they're fairly close. But to the left of the origin, it's actually almost the opposite. Okay? Another thing I want you to notice is the slopes here. How does the slope right here compare to the slope right here? And I could add another one in here. How about there and there? As we get closer to the origin, the slopes are getting smaller, right? They're getting steeper as you get further from the origin. But the derivative, the values on the derivative are staying roughly the same. They're staying at positive 1 to negative 1. So it's not showing that the slopes are getting bigger as you get further away from the origin. So that's another thing in the derivative that doesn't really match up with what it should be. So just that right there shows you that the derivative of sine of x squared is not cosine of x squared. It's going to involve this right here, but we're going to have to multiply by something here to fix it. So the derivative of sine of x squared is actually 2x times the cosine of x squared. And now if you look at this blue function here, notice that as you get further from the origin, the peaks and valleys are higher and lower to show that the derivatives or the slopes are getting bigger. And notice also that at 0, as Cole pointed out, at 0 we have a point at 0 on the derivative also because it has a horizontal tangent. And it's negative on this interval here where the derivative where the slope is negative. So we have a different function here that's close to what we thought it would be. It actually involves what we thought it might be, but it has something else in there. Anybody want to guess where that 2x came from? Haley? It's the derivative of the x squared. Exactly. So the chain rule is going to allow us to take the derivative of compositions of functions. This right here is a composite function. Oops. This right here is a composite function because it's the sign of another function. So if we said that f of x, I probably shouldn't use that because I already have f of x. Let's say I have r of x equals the sine of x, and I have h of x equals x squared, then this would be what in terms of r and h? It would be r of h of x, the composition of r and h. So this right here, the chain rule, is the main reason that we spent a little bit of time earlier in the year talking about the compositions of functions, because it allows us to find the derivative of the compositions of functions very easily. Okay, so let's look at an example here, and we're going to do this using substitution. We're going to use this using ideas that you already know but wouldn't necessarily know to put together yet. So the first thing I'm going to do to find the derivative of the sine of x squared, which is what we had in the last problem, right? The picture of the last problem. Yeah? The first thing I'm going to do is I'm going to take this x squared here and I'm going to replace it with a u. So I'm going to say u equals x squared. And then what I end up with is y equals the sine of u, right? Why might I do something like that? Why might that be useful to us?
Gets rid of the squares.
It gets rid of the squared, right? It simplifies it. It simplifies it to a function that we know how to take the derivative of. Okay? The only problem is, let me write the derivative part first. We can take the derivative of this and we get cosine of u, but we're not taking the derivative with respect to x. We're taking the derivative with respect to u. So what we just found is actually dy du. Now I probably should have said this in the beginning, but what we want to find is dy dx. We want to find the derivative with respect to x. So I got the dy part good. I don't have the du part the way I want it. So any ideas how I could incorporate the dx into this with what I have written here? What we're going to do here is we're going to take this equation and we can take the derivative of u with respect to x. So over here we get du dx is equal to 2x. Now, why is that useful? Cole?
Can you plug that into the cosine?
No?
Okay.
We could plug this into it, but we don't have a du dx over there to plug it into. Yeah?
We can multiply the cosine of u times 2x.
Okay, and why would we do that?
2, because when you multiply dy of du times du of dx, the du's cancel out and you get
Oops.
dy over dx.
Okay, so these are the two derivatives that we just found. And these differentials here can almost be treated like numbers. There are actually some rare situations where we can't treat them like numbers, but this is one where we can. So if we take dy du times du dx, before we even write down what that's going to be, what could happen here with the du's? They cancel each other out. And so that's going to be equal to dy dx. So the derivative of y with respect to u was cosine of u. The derivative of u with respect to x was, 2x. And so now what we have is dy dx. We do have a problem though. Let me clean this up a little bit here. I'm going to slide that over. what's our problem? Dalla? Yeah, the u is still here. So I gave you a problem, a function y in terms of x. There's no reason that we should write our answer in terms of some variable that we just made up. Okay? So we don't want this u in here. We want to get rid of that. We got rid of the du's, which was good. We introduced this variable u, which means that we have to get rid of this variable u when we give our final answer. So we're going to replace the u with x squared, because u equals x squared, right? So we're going to say this is the cosine of x squared times 2x. Does this look familiar? When I showed you the graph, that was the derivative that I showed you, right? Does that make sense what we just did there? Let's go ahead and do another problem just like that, using the same ideas here, using substitution. So basically what I want to do is I want to simplify the function into something that I know how to take the derivative of. And I think this is a fairly obvious one. What do you think we should let u equal here? 2x plus 1. All right, now, usually when I'm doing a problem like this, right off the bat, when I figure out what u is, I'm also going to figure out what du dx is. And in this case, that's going to be what? 2. So the derivative of u with respect to x is going to be 2. All right, now, we let u equal 2x plus 1 so we could simplify this. So what's this going to end up looking like? Y equals u to the third power, or u cubed. All right, so then that means that dy du is 3u squared. So we're just taking the derivative of u to the third power with respect to u. And so what we want to find here, dy dx, is going to equal dy du times du dx. You don't necessarily have to go through all these steps every time. I just want to make sure you see where this is all coming from. And these du's here are going to cancel each other out. And so that's going to equal, what is dy du? 3u squared times du dx, 2. So there's two things I'm going to do in this next step here. I'm going to go ahead and multiply the constants together. 3 times 2 is 6. And then I also want to get rid of the u. So instead of u, I'm going to put 2x plus 1. I just want to show you here a way that we could have taken the derivative before. So before today, before you learn the chain rule, here's what you would have had to do. You would have had to figure out what 2x plus 1 times 2x plus 1 times 2x plus 1 is, which is not too bad because you know the binomial expansion theorem, right? You may not know it by name, but you know how to expand that. So it would be, what's that? Yeah, you'd use the Pascal's triangle stuff. So this Pascal's triangle, the third row is 1, 3, 3, 1. So you would have 1 times 2x to the third power plus 3 times 2x to the second power times 1 to the first power plus 3 times 2x to the first power times 1 to the second power plus 1 times 1 to the third power, which is just 1. So you could actually, in theory, expand it even if it was something like 2x plus 1 to the 7th power, using Pascal's triangle and what you know about binomial expansions. At this point, it's fairly easy to find the derivative, right? Dy dx is going to be what? 24x squared plus 24x plus 6 plus 0, right? Is this the same thing we got in the last problem? Hopefully. Let's see. If I factor out a 6 here, then I would get 4x squared plus 4x plus 1. And that factors to 2x, nope, sorry, 4x plus 1 x plus 1. Did I do that right? No. I don't like factoring these. Yeah, it is 2x plus 1, isn't it? I should have known that because that was the answer in the last one. Is this the same answer we got in the last one? Yeah. So we get the same answer. The problem is you have to use some crazy binomial expansion theorem to figure out what that's going to be, especially when that power gets really big. And it becomes an even bigger problem when we're not dealing with binomials that we want to expand, but maybe trinomials, or maybe trig functions, or maybe exponential or logarithmic functions later on when we learn how to differentiate those. So what the chain rule does is it allows us to use the composition of functions to take the derivative of somewhat complex looking functions and make them much simpler. I like this cartoon. This is kind of the way I learned the chain rule. So you start by differentiating the mother and you leave the baby inside, and then you differentiate the baby. So basically what it's saying is you take the derivative of the big function, the outside function, or what this cartoonist is calling the mother function. You take the derivative of that, keeping the inside function the same, keeping the baby the same. And then once you've done that, you take the derivative of the baby function, the inside function, and you multiply by that. So using that idea, let's do the same problem here, but we're going to do it without substitution, and we're going to use it using the chain rule still. So instead of using substitution and introducing this u variable, we're going to say dy dx equals, so we're going to differentiate the mother function. Well, what would you call the mother function here? The x cubed function, right? So the cubed function. So we're going to differentiate that, but we're going to keep the baby inside. What are we calling the baby here? 2x plus 1. So we're going to take the derivative of the big function, the mother function, but keep the baby inside. So that would be 3 to the second power. You guys see where I'm getting this? So I just took the derivative of that like I would any third power, any variable to the third power. But I kept the baby inside, and then we have to multiply by the derivative of the baby. So we differentiate the baby. What's the derivative of the baby? 2. And this is much simpler then. We just multiply the constants out front, and we get the same thing. Now, what we just did is technically substitution without writing down the substitution. What we did is we said, okay, we're gonna put some other variable in here, and we're gonna take the derivative with respect to that variable, and then we're gonna plug it right back in right away. So we took the derivative of it, got 3u squared, but then 2x plus 1, put 2x plus 1 in for u right away. And then we took the derivative of that inside function, the u function, and multiplied by that. Does that make sense? So when you're using a chain rule, most often it's going to look like this. I will ask you to do the chain rule where you're using substitution and tell me what you want to let u equal. Or you could use really any variable that's not already being used. You could use t or x. Well, a lot of times you won't be able to use x. You could use z or a or whatever. Typically we use u because a lot of the other letters are reserved for other things. So a lot of times when we're using substitution in calculus, it ends up being what's called u substitution. Okay, so let's do this one two different ways. We're going to do it with substitution and then without. The first thing we need to understand about this problem is that sine to the third power of x means something that is not immediately obvious. So let's rewrite it to make the math a little bit more specific. What does this function mean? It's sine of x to the third power, right? You guys agree with that? Now, this problem is actually really, really similar to the last one because it was just a function to the third power. So the derivative, we're going to use u equals what? Okay, so u equals the sine of x, which means that the derivative of u with respect to x is going to be what? Cosine of x. And we can rewrite y then, y equals u to the third power. Because we said that sine of x is equal to u. Which means that the derivative of y with respect to u is 3u squared. So the derivative of y with respect to x, I'm going to do a few things at the same time here. We're going to have 3u squared times cosine of x, but we know that u is what? Sine of x. So we're going to say 3 sine of x squared, or sine squared x. And this is a mechanics thing here. If we put the squared over here after the x, what would that mean?
Sine of x squared.
Yeah, so what would we be squaring? We would be squaring the x. So it's kind of funky notation here, but we put the cube on the sine to show that we're cubing the sine function. But we cube it after we take the sine of x. So we have 3 sine squared x times what? Cosine of x. So we get dy dx by multiplying dy du times du dx. And that's going to be 3 sine squared x times cosine of x. Does that make sense? Do you think you could do this problem without using substitution? So dy dx is equal to, we're going to differentiate the mother and keep the baby inside. So what's the mother function here? The cubed function, right? So it's going to be 3 times something to the second power. And what are we going to have inside here? Sine of x. The sine of x was our baby function, right? You guys understand what I mean by mother and baby functions? I will probably, for the rest of the year, refer to them as mother and baby functions, so get used to it. Times the derivative of the baby. What is the derivative of sine of x? Cosine of x. And then just clean it up a little bit, and it looks exactly the same as we had when we did the substitution. For now, when you're doing the chain rule, unless I tell you or the problem in the book tells you one way or the other, you can use substitution if you want. You don't have to. A lot of people feel more comfortable using the substitution because it helps keep your work straight. I will tell you, we'll start using the chain rule. This would be a 2-level chain rule problem. We could have a 3 or 4 or 5 level chain rule problem where we have to do it several times. And we'll look at some examples of that probably tomorrow. Let's go ahead and do one more. Do you guys want to do substitution on this? You want to just do it without? Okay, let's do it without. Without substitution. Okay, so the derivative of y with respect to x is equal to 5 Okay, so that's the derivative of the mother function with the baby staying inside. Now what? We have to differentiate the baby.
Do you want to say it?
Sure.
6x minus 2
Like that?
in parentheses.
What'd you say?
In parentheses.
Yeah. The parentheses are important because if you don't have the parentheses there, this negative 2 isn't being multiplied by the derivative of the mother function. Again, you could clean this up a little bit. I would probably put the 6x minus 2 out front here. There's certainly no reason that you would have to expand this. and figure out what 3x squared minus 2x plus 4 to the fourth power is, because that would be a little ridiculous. Any questions about this? Let's see what else I have for you here. This is what we were going to do on the last one. That's blank. It's done.